Alright guys, so just going to do a quick lesson on diffusion and effusion. This will actually finish up our gas unit. We're going to keep this pretty simple. First you need to know the difference between diffusion and effusion. Diffusion is the movement of a gas from an area of higher concentration to an area of lower concentration, and effusion is the movement of a gas through a small hole. And so an example of diffusion might be if you left open a perfume bottle in the corner of a room. Well, over time, the gas particles of that perfume are going to spread throughout the room, and the people on the other side of the room are going to be able to smell that perfume. That is diffusion. Effusion is movement through a small hole, so this would be just any kind of situation where you have a very tiny opening. This could be why a balloon deflates over time. It could be why a tire deflates over time. There's a very small hole, and air gradually escapes through that hole. They share a lot of commonalities. It's the movement of gases from higher concentrations or higher pressures to lower concentrations. And so there's a lot of similarity there. The mathematics we're going to apply to this, and here's Graham's law. It states that the rate of gas 1 divided by the rate of gas 2 is equal to the square root of the molecular mass of gas 2 divided by the square root of the molecular mass of gas 1. And so I use different colors here to kind of point out the relationship. So you can see that the rate of the first gas is on the numerator of the left side, and its molecular mass is in the denominator of the right side of the equation. What this law basically states is that the heavier the gas, the slower the rate of diffusion will be. So when we say the heavier the gas, we're talking about molecular mass, the molecular mass of the molecules of the gas. So the heavier the molecular mass, the slower the rate of diffusion will be, is what this law is stating. And we can make some we're going to do simple mathematics with it. We're going to keep the problems pretty basic. But if I tell you you've got nitrogen and you've got carbon dioxide, and I ask you which one of these diffuses at a faster rate, that's an easy question to answer. All you have to do is figure out the molar masses of these two gases. Molar mass of nitrogen being approximately 28 grams per mole, molar mass of carbon dioxide being approximately 44 grams per mole. And so the nitrogen is going to diffuse faster, relatively speaking, to the carbon dioxide, which will diffuse slower. And so if it's just which is faster, just look at the molar masses and pick the one with the lightest molar mass. We're going to go beyond that, though. We're going to ask and work through some actual rate problems. So let's set up one of those. So here's a question: how much faster will nitrogen effuse than carbon dioxide? So now I'm just asking which will effuse faster. Now we're asking about to compare their rates. And so here's how you're going to work this. We're going to keep these pretty easy. And so we have our equation of rate 1 over rate 2 is equal to the molar mass of 2 over square root of molar mass of 2 over the square root of the molar mass of 1. Here's how I suggest you work this. And so if you're looking for how much faster, we know that this is going to be faster. We know that this is going to be slower. And you know that because this has the lighter molecular mass of 28 grams per mole versus 44 grams per mole. And so here's what I recommend you do. You take your lighter particle and you make that the rate 1. You make that the rate 1. Because what you're going to end up doing here is you're really looking at a proportion here, and we don't have a rate. There's no rate given in the problem. All you have are molar masses. So you can plug in molar mass here, and you can plug in molar mass here, but you have no rates to plug in. So we're missing a variable in this problem. Well, the key to that is that you've not been asked to find the actual rate. You've simply been asked to find the relative rate, how much faster of one gas than the other. So we're not looking for an actual rate, but a relative rate. And so what we're going to do is we're going to make the rate of the slow one 1. We're going to make the rate of the slow one, in this case carbon dioxide, we're going to set its rate equal to 1. And so let's plug it in. Let's set the rate, and we're going to make that rate 2. We're going to make that the denominator, because when you divide by 1, you get a whole number. So that's why we're going to put that as our 1 there. So this is going to be our rate of nitrogen, is what that's going to be. And then we're going to plug in our molar mass. So this is going to be a molar mass. This would be CO2 on the top and molar mass of nitrogen on bottom. So square root of molar mass of 44, square root of the molar mass of 28. And now you just solve this. Rate of nitrogen is equal to the square root of 44 over the square root of 28. And that gets you 1.25. All right, and so this is our answer. It is 1.25 times faster than CO2. That's your answer, because we said that CO2, we made its rate arbitrary. We made CO2's rate 1. And so if the CO2 rate is 1, then the nitrogen rate is 1.25. Well, it's 1.25 times faster than CO2. And so that's how I recommend you set those up. Now we can also solve a problem where we actually find the actual rate, and we can do that as well. So here's another question. What is the rate of effusion of oxygen if helium diffuses at 2.4 milliliters per minute? And so we're just going to plug in here. We can get the molar mass of oxygen, 32 grams per mole. Molar mass of helium is 4 grams per mole. And we have a rate for helium. So we have 3 of the 4 variables we just need to plug in. Now where do you plug them in? It doesn't really matter which one you make rate 1, which one you make rate 2. However, I would make the one I'm looking for rate 1, since it is a numerator, and we'll just multiply the rate 2 across to solve out. So if we make rate 1 what we're looking for, which is what is the rate of oxygen, then it's going to be rate of oxygen over the rate of helium equals the square root of the molar mass of helium divided by the square root of the molar mass of oxygen. And then when I multiply both sides by the rate of helium to get rid of it, now I've got rate of oxygen as a numerator. So there's my rearranged equation. Rate of oxygen is equal to molar mass of helium square rooted divided by the square root of molar mass of oxygen times the rate of helium. So now we just plug in to our calculator and get our answer. So square root of 4 over the square root of 32 times the rate, which was 2.4 milliliters per minute. And that is equal to 0.85 milliliters per minute as our rate of oxygen. And you can do a quick logic check on that. The helium, which is lighter, should diffuse at a faster rate than oxygen, which is what this gives us. Oxygen is a much slower rate. It's a much heavier molecule, and so we get a lower rate for it. Okay, so use these examples to help solve the questions in your practice, and I will see you tomorrow.